Good morning, friends. I am here, Dr. Dwivedi, professor from Institute of Aeronautical Engineering, Hyderabad, India. I am in the process of giving lecture on aircraft stability and control. Today, I am in the lecture number 17, which is related to lateral and directional stability of the aircraft. I will go first with the introduction of the lateral and directional stability. In this, longitudinal and lateral direction motions are independent of each other. Means the longitudinal motion means pitching. Pitching is called the longitudinal motion. So this pitching and rolling and yawing. This rolling and the yawing, that is called the lateral and the directional. These lateral and directional motions are coupled with each other. So, lateral directional motions is assumed to consist of roll and yaw rotation in and y-axis translation. So, in this roll and yaw and the y-axis translation. Okay, so what is the meaning of? I have to explain here. What is the roll? When the wings ailerons are applied, so if you apply the aileron, this thing upward and here downward, the right wing will go down. Once right wing is going down, this side lift is high, this side lift is less. So there will be a drag. Drag will be pulling this thing like this. So as you roll the aircraft, yaw will be there. That is why rolling and yawing both are coupled. And this y-axis translation means rolling, yawing and sidewise. These three positions are called the lateral and directional motion. And in longitudinal, pitching and forward and two pitching, x direction and this z direction. These three motions are in the longitudinal motion. So, these two rotations and the translations are typically coupled, that is, they occur together. Just now I have explained the roll and yaw. Both are coupled. If you roll, a yaw will be there. If you yaw, roll will be there. You cannot make different. We will now expand the applied lateral directional aero forces and moment terms with conventional aerodynamic coefficients. Here now I am going to discuss about lateral directional applied forces and moments. We will now expand the applied lateral directional aero force and moments terms with conventional aerodynamic coefficients in the stability axis. We have now the side force, it is Fay, 1S, but this S is stability axis. So we will be only writing Fay. La1S is equal to La, this is the rolling moment, L is rolling moment, and Na1S, this is Na, this is the yawing moment. So these two moments, and this is the force, and this is the moment. So these three things are called lateral directional applied forces and moments. So there is one force and two moments in lateral directional applied forces. Because the body axis, stability axis, will be used consistently for this steady state analysis, the subscript here 1S here in all the places 1S, we are not taking further. So if Fay means it is Fay 1S, La means La 1S, Na means Na 1S. So these things we are neglecting for further studies. Now aerodynamic side force, it is very important that aerodynamic side force act along the number 2 stability axis, that is positive out the right wing and may be expressed using the side force coefficient Cy as Fay is equal to Cyqs. So, side force. If aircraft is flying like this and some force is generated towards the y-axis, aircraft will start moving in sideways. So, if it is going towards the right, it is a positive, and if it is going towards the left, it is the negative. So, this convention we have to follow in the further studies. So, this side force F is a function of angle of side slip beta, aileron deflection angle delta A, rudder deflection delta R, angle of attack alpha, Mach number M, and Reynolds number R. So this depend upon these parameters, and it will vary if these parameters are varied. Here this we can see about the side slip angle, very important here. This you can see here, a positive side slip angle beta is defined in this figure. It can be easily remembered as positive B is wind in the rear ear for the pilot, right ear. Right ear, if the wind is coming from the right side of the pilot, we can see that aircraft is, this angle is positive. So here we have seen that pilot is here, assume it is sitting here, and aircraft is moving in this direction, and wind is coming from this direction. So pilot here, so this is the right side. So pilot is experiencing the wing from the right side, and if it is like this, it is a plus beta. So plus beta means the wind is approaching from the right side of the pilot. Thus we can see that it is a positive side slip angle. So now this Cy, that is the side force, Cy is by using the Taylor series, Cy naught plus Cy beta into beta plus Cy delta A into delta A plus Cy delta R into delta R, where beta is a side slip angle, delta A is a deflection of aileron, and delta R is a deflection of the rudder. As I told you that if you move the ailerons, rudder will also be required to be moved. Both are coupled. You cannot have separate. So always in this lateral and directional study, ailerons, angle of ailerons, deflection, and the rudder deflection have to be considered at each cases. Here Cy naught is the value of Cy for beta, delta A, delta R. When all are equal, the value which we are getting of this is a Cy naught. It is a coefficient of side force at zero angle of attack. Now we have to find the Cy beta. In the change is the change in the side force, that is Cy coefficient because of a change in side slip angle at constant angle of attack. Means aircraft should be constant angle of attack, and how much side force is changed when the side slip angle is changing. Suppose when the side slip angle is 1 degree, you are getting side force 1 kg. When your beta or side slip angle is 5 degree, you are getting the 2 degree. So how much change? 2 minus 1 divided by 5 minus 1. So this is your derivative for Cy beta. It has an important influence on Dutch roll dynamics. Very, very important that we have to understand that these parameters are very much implemented for Dutch roll elimination of Dutch roll effect of the aircraft. The vertical tail is the primary aircraft component that influences this derivative. So this vertical fin, you see, this is the vertical fin here. This vertical fin is a very important component which will affect this side force. We will be discussing. So Cy beta is normally negative because positive side slip angle will typically results in a side force along the negative axis out the left wing. So Cy beta is normally negative because positive side slipping. Okay, just you can see here I am giving. So here this flow is coming like this and hitting here at the vertical tail. This hitting of the force will generate a force in this direction. In this direction, left side of the wing. So this left side is negative and right side is the positive. So a positive side slip angle, the angle when aircraft is going like this positive beta, so this angle is beta, this positive angle is hitting in this vertical fin, and this, after hitting this, a force is generated towards the left side, so it is always negative. So positive will provide a negative side force and negative will provide a positive side force. That we have to very much clearly understand, otherwise it will get confused. So negative side slip angle will result in a positive side force. The vertical tail can be thought of as a vertical wing with the side slip playing as analogous role to the angle of attack. So it is just like a wing and angle of attack. Same way, side slip and the vertical tail, vertical fin, both are acting in the same way. The angle of attack is equivalent to the side slip angle in the vertical tail. Method to estimate Cy beta, coefficient of side force. So a method to estimate Cy beta based on aircraft configuration begins with the definition of the aero side force acting on the vertical tail using the side force coefficient. So FAY vertical tail is equal to Cy Q and S. So in this way we can see that. So if we differentiate this equation 2.1 with beta, so delta F AY vertical by tail beta is equal to dou Cy vertical tail by dou beta Q1S. We can write here CYB vertical Q&S. So this CYB can be achieved as done in the longitudinal stability case. So here we can get here that Cy beta vertical tail is equal to minus CL alpha vertical tail 1 minus D by D beta neta vertical tail S vertical tail by S. So here this sigma is the sideways angle analogous to the downways angle, and neta vertical is the ratio of the Q vertical tail by Q infinity. This is the dynamic pressures of vertical tail, and here D epsilon by D beta, it is a sideways derivative and it's very small. Here CL alpha vertical can be taken similar to the CL alpha by putting and replacing H to V. So this we have done in the earlier. CL alpha is equal to CL alpha WF plus CL H NH SH by S 1 minus D epsilon by D alpha. Okay, this we have done already. So CL alpha is equal to CL alpha 1 plus 57.3 CL alpha pi EA aspect ratio. When computing CL alpha vertical tail, equation 2.5 may be used with the following approximation for the aspect ratio of the vertical tail. So aspect ratio of the vertical tail is equal to 2 into height of the vertical tail whole square divided by S vertical tail, area of the vertical tail. So like this, here we have to find out the aspect ratio by using this equation. The equation provides a rough estimate for the effective aspect ratio of the vertical tail, where h vertical is height and s vertical is the planform area of the vertical tail. Now the second derivative is cy delta a. So cy delta b we have already done. Now the delta a is reflecting the deflection of aileron. Is generally insignificant or negligible. However, it can be significant if rolling moment is generated with control surfaces that are in a close proximity to the vertical surface. For example, on the F111 aircraft, differential deflection of the left and the right stabilizer was used to produce rolling moment when the wings were in the swept back position. This produced a differential pressure on the vertical tail, which resulted in a side force as illustrated in the below with B1 aircraft. This you can see here. Explanation is very important and how this thing can be achieved. This you can see here that these are the horizontal tail. Here also. So if you want the rolling motion, then if you want to make this thing lift down and here you want more lift, the rolling will be there in this way. This will generate a side slip here and this force will be generated. So it will try to recover its position. Okay, so right stabilizer, leading edge up, increase the lift and lower pressure on top surface. So here lift is increased and upper surface the pressure is less. Here what happens? The left stabilizer, leading edge down, decrease the lift and higher pressure on the top surface. So the right side lift is this much and left side is this much. So there is a difference in L1 and L2. So L1 minus L2 is equal to L and L into this distance X. So L into X. This much moment will be in this direction, anti-clockwise direction. So how this aircraft will be stable? This stability will be achieved by the help of this vertical stabilizer or the vertical fin. So as it is moving in this direction, the relative wind of this direction will be higher. So a lift will be generated in this direction, a force. This force into this center of gravity, this Y. So this vertical lift LV into Y is equal to this L into X. So if like this, your aircraft will be stable, and the purpose of the vertical stabilizer is to do like that. So in this way it is stabilizing. Now the next derivative is rudder derivative. So the variation of the side force when we vary the rudder delta or deflection we do. So the derivative Cy delta R is positive because a positive rudder deflection, that is trailing edge left. Very important that positive means this trailing edge. This is the rudder here. This is the trailing edge. This you can see here. This is the rudder and this is the left side and this is the right side. So if trailing edge is left in this way, will generate a side force along the positive Y. So if you make like this, a force will be generated in this direction. So the positive deflection will generate a positive force. But in the rolling, it was opposite. Okay, in that Cy beta, it was opposite. Cy delta A also, it is opposite. But here, it is not same. It is, if you deflect positive, a force in the positive direction will act. The size of the vertical tail in relation to the wing, along with the aspect ratio and sweep back of the vertical tail, determines the magnitude of this derivative. So, how much this derivative should be there. It depends upon the vertical tail size along with the aspect ratio and how much sweep back of the vertical tail. So this is the sweep back. It is not straight. It has got some angle. So this angle is also important to achieve the aircraft stability. And determine the magnitude of this derivative. These parameters are very much essential. Now aircraft rolling moment we will discuss. So now we have completed the aircraft force, that is side force, and they are all three derivatives. This is the Cy beta, Cy delta A and Cy delta R we have completed. Now I am going with the another moment which is the rolling moment, because in the lateral and directional equations in the motion we have the one force and the two moments. So I have completed the one force. Now I am going for the first moment, that is the rolling moment, and it is represented by capital L. Aircraft rolling moment acts about the x-axis and may be expressed using the rolling moment coefficient, that is LA is equal to CL Q bar SB. So here we have to understand that CL is a coefficient of rolling moment, Q bar is a dynamic pressure, S is the area, and B is the span of the wing, S is the surface area of the wing. Okay. So the rolling moment coefficient CL here, this CL is depend upon the beta, side slip angle, delta A is aileron deflection, delta R is rudder deflection, alpha is angle of attack, and M is the Mach number, and RE is the Renault number. So these are the parameters which will affect the CL. So this dynamic pressure Q and the CG also affect the rolling moment coefficient CL. Using the Taylor series in first order, we have the coefficient of moment CL is equal to CL naught plus CL beta beta plus CL delta A plus CL delta R. Here CL naught is the value of CL for beta, delta A and delta R when these all three parameters are 0, and whatever the value you are getting for coefficient of rolling moment, that is called the CL naught. And for the symmetrical aircraft, CL naught will be 0. However, it may not be typical for aircraft with long, slender forebody where asymmetric vortex setting is present. So if your wing are symmetrical one, so CL naught will be 0, but if the aircraft is very long and body, the fuselage is very slender, then it may not be 0. Now this lateral roll static stability derivative, now CL beta, like Cy beta. Now first derivative of the this lateral moment is CL beta. It is also sometimes called the dihedral effect. This is dihedral that we will be seeing very soon. What is the dihedral? The sign of the CL beta must be negative if an aircraft has a roll static stability. So to have the in the rolling, if the aircraft is static stable, CL beta should be negative. That is the very much important. A negative CL beta implies that the aircraft generates a rolling moment that rolls the aircraft away from the direction of the side slip. So what is the meaning of CL beta negative? CL beta negative means the aircraft generates a rolling moment that rolls the aircraft away from the direction of the side slip. Means it will roll away from the direction of the side slip. Okay, so that is the important characteristics of the CL beta negative. So there are 4 aspects of aircraft design primarily influencing the CL beta. First one is the geometrical dihedral. wing position, then CL beta, these equations are there, and contribution of the vertical tail. So these are the 4 aspects by which the CL beta gets influenced. So first one is the effect of the wing geometrical dihedral. So dihedral means, if you see here with this horizontal, there is some angle upward. So if the tip is above the root and the angle which is making from the horizontal, then we say that it is a dihedral. So this dihedral angle is given name as a gamma. The wing dihedral angle as shown here, this is the dihedral angle gamma. So the wing dihedral angle, that is gamma, provides a significant negative contribution to CL beta. So just now I have told you, to have a stability in rolling, this should be negative. CL beta should be negative. If the CL beta is negative, 100% your aircraft is stable in rolling moment. The larger the dihedral angle, as much you have the more gamma, the more negative rolling moment will be results from a positive side slip angle, and the more positive rolling moment will result from a negative angle. So as you have the larger dihedral angle gamma, the more negative rolling moment will be resulting from a positive side slip angle. Means if the beta is positive, CL beta will be negative. That you have to keep in mind. If it is like this, then only you will get the stability. And the more positive rolling moment will have the more negative. If CL beta is positive, beta will be negative. These 2 things we have to understand. So I think it is very much you are able to understand about the beta here. In this diagram, if you see here, aircraft is moving in this direction and your wind is in this direction. So this angle, because it is going from the right side of the pilot. So it is the right side. Okay, right side of the pilot, then it is a positive beta. If it is positive beta, aircraft will generate a CL beta negative. Okay, so that is very important discussion. This occurs because the wing towards the relative wind experiences a higher angle of attack than experienced by the opposite wing. So how and why it is happening? Just you can see in this diagram, this is the beta in this direction and it is a positive. The right wing, this is the right wing. Right wing is experiencing more angle of attack. Due to this more angle of attack, more lift is generated here, and the left wing will generate a less lift. The moment will be in this direction as it is shown in this. Rolling will be, the left wing will be down and right wing will be up. Okay, so always you see wing is coming from this direction and rolling will happen in this direction, opposite. So CL beta is negative here. CL beta is negative. That we have to very much understand. The dihedral contribution to CL beta may be estimated with the following approximation, where lambda is the wing taper ratio and is defined as lambda is equal to CT by CR, where CT is the tip chord and the CR is the root chord. So what is the meaning of tip chord? So this is your fuselage. This is the tip. So this is called CT and this is called CR. So this lambda is equal to the ratio of tip chord to the root chord, and it will be always less than 1. So CT is the tip chord and the CR is the root chord, and the CL beta dihedral we can calculate by minus 1 by 6 CL alpha wing gamma 1 plus 2 lambda by 1 plus lambda. This is the equation. Several fighter aircrafts like F-104, F-16 are designed with a negative dihedral. So what is the negative dihedral? It is also called the anhedral. Negative dihedral. Fighters aircraft have the negative. I will give just an example. So if this is called the negative, this is called the negative. If you see, this is the gamma and this is the negative gamma from horizontal. Means it is tip is down than the root. So it is called the negative. So this provides a positive contribution to CL beta and normally used to reduce the magnitude of the roll stability, because too much roll stability, a large negative value of CL beta will have an adverse influence on Dutch roll, engine out and crosswind landing characteristics. So in Dutch roll, what happens if you have the more CL beta, the response will be very fast. So if aircraft is flying like this and wind has come from this direction, it will do like this very fast. That much fast we don't need, especially during the crosswind landing on the runway, or when aircraft is experiencing a Dutch roll or engine out, one engine is failed. That time if aircraft is experiencing a very heavy amount of negative value of CL beta, it is very dangerous. So we should not have a very high dihedral, so that this Dutch roll and this engine out and crosswind landing can be avoided. So now effect of the wing position on the aircraft. It is also very important parameter. You see, in this aircraft we have the down wing. Some aircraft have the higher wing, some are having the mid wing. So the down wing has got some other advantage, upper wing, high wing has got some other advantage. So every type of configuration of the wing location has its own value, and this will be discussed in this class. A high wing position will provide a negative contribution to CL beta. If the high winger is there, the first case here, in high winger aircraft, it will provide a negative contribution to the CL beta, and we need the negative to have stability. A low wing position will provide a positive CL beta. So here it will give positive, it will give negative, and a mid wing will be neutral. Okay. So if you want to put the neutral, it will not give any rolling stability. So high wing experiences, you will see here, the high wing is there, flow is coming from this direction. This will have more upward lift and this will have the downward lift. Here angle of attack is more and here angle of attack is less. So the which side the aircraft is, the air is hitting, that wing will give lift. So roll will be there, and this roll will have in this direction. Okay. So increased lift and the reduced lift in other side. So high wing experiences high angle of attack towards the relative wind, and low wing produces low angle of attack in the wing fuselage interaction. So this high wing produces negative rolling moment. So here you will have CL beta negative. So it is a stable. Okay, and here it is unstable because CL beta is positive. So if the CL beta is positive, it is unstable. So most of the fighter aircraft, they will have the lower side. Here also if you see Boeing and all, they also have the lower side of this thing, so that it is very easy to land during this bad weather in the runway and other things. Now the second parameter is effect of wing sweep. of the aircraft. This you can see here, the wing is here swept. This is the sweep angle here. This is the sweep angle. So if you see here, a side slip angle results in a side velocity that can be broken into two vector component, normal and parallel to the leading edge of each wing. So if you see here, this is the right wing and this is the left wing, and this beta is positive because wind is coming from the right direction. This side you will have more velocity. This you can see here, and here you have less velocity. Okay, this value, if you see this value here, and this vertical velocity is high here, and here is very low. So this side lift will be more, and here lift will be very less. Comparing to this, lift will be reduced. A rolling movement in this direction will take place. Aircraft will roll from right to left. With aft sweep, the wing towards the velocity vector, the leading edge has a larger normal velocity component than the wing opposite. As a result, the upstream wing will produce more lift than the downstream wing, resulting in a rolling moment away from the side slip direction. So this negative contribution of CL beta. So this is giving CL beta as a negative, means stable. So if you want the aircraft to be stable, the sweep is helping to make the aircraft stable. A simplified estimate of the wing sweep contribution to CL beta is presented in equation 2.11 for aft sweep. The reference is from US Air Force Academy glider design program, and this CL beta wing sweep is equal to minus 2 CL wing YAC wing by B sine 2 sweep angle. This is the equation for this, and this is given by US Air Force Academy, where YAC wing is the positive Y body axis distance to the wing AC. This leading edge angle of the sweep of the wing leading edge is in radians, and B is the span of the wing. Here this CL beta wing sweep depend on the wing lift coefficient. The analysis is reversed for forward swept wing. Forward swept wing provides a positive contribution to the CL beta. This equation 2.11 may be used as estimation of this contribution by simply dropping the negative sign. So if you want to do for the forward sweep, you just avoid this minus, you make the plus. Everything will be same. So positive sweep, the forward sweep and backward sweep, both you can do the analysis, and only the sign of this thing will change. Now I am going to discuss about the effect of the vertical tail. So a positive side slip angle will result in an aerodynamic force on the vertical tail in the negative y-axis, because the vertical tail is normally above the x or rolling axis of the aircraft. This aerodynamic force produces a negative rolling moment that results in a negative contribution to CL beta. The larger and the higher the vertical tail, the more negative the contribution of CL beta. An estimate is given here that CL beta vertical is equal to zeta V by B Cy vertical. This is the equation where ZV is the vertical distance up in positive direction. However, at higher angle of attack, the ZV can be negative as the angle of AC of the tail is going below the CG, as you can see in this figure. So this we can see here that aircraft is flying with the free stream velocity of V infinity. Here is the vertical tail aerodynamic center. Here this is the horizontal line, and from here the distance is ZV. So illustration of a positive ZV at a low angle of attack. If it is flying with some 8-9 degree angle of attack, it is positive. But when aircraft angles of attack is changed, this position of AC is below this. So this is the negative. So if this is become negative, it has gone below the illustration of a negative ZV at a high angle of attack. So at higher angle of attack, this will be unstable. And this is at low angle of attack, this case is stable. So we have to think that what is the location of the aircraft, and accordingly we have to see that aircraft is behaving properly and the stability of the aircraft is maintained as per the required standard. So now ZV may be estimated with the following equation of the low angle of attack. So this ZV is equal to 1 by 3 H vertical tail, 1 plus 2 lambda vertical by 1 plus lambda vertical, dividing by B. So we will get CL beta tail, vertical tail is equal to minus ZV by B, CL alpha vertical tail, 1 minus G, 1 minus D sigma by D beta, neta vertical tail, S vertical tail by S. So T tail will increase the CL beta vertical because it increases the aspect ratio of the vertical tail by minimizing the tail vertices. So now I am ending here. So this is my references, HOUT TR, Introduction to Aircraft Flight Mechanics by AIA publication, Nelson RC, Flight Stability and Automatic Control, and also I am referring NPTEL lectures of Aircraft Stability and Control by Professor A.K. Ghosh, IIT Kanpur. Okay, thank you very much for this joining my class. Hope you are understanding very well, and please rejoin for my next class. Okay, thank you very much, and watch my videos, and my any queries you can ask to ydwivedi@gmail.com. Any questions can be asked in this Gmail. Thank you very much for attending the class.
Like, share and subscribe. Hit the bell icon for more updates.